All right, so far we've been talking about the study of motion in 1D, but now we're going to get into the next chapter and start to look at kinematics in 2 dimensions. And the motivation for this is that in 1 dimension, the problems that we can examine and the things that we can study are not terribly useful when compared with real life. You know, in other words, the things that we're limited to, the motion in 1D that we're limited to studying, doesn't really happen all that often in the real world. You could probably think of a couple examples of 1D motion. The first one that comes to my mind is driving a car, but driving a car very simply up and down the street, never turning, so moving forwards and backwards. Another one certainly is if you decided to throw a ball straight up into the air. For example, if you were throwing a basketball up through the hoop, and then as it came back down, it passed through the hoop again, so that ball went straight up. That's 1D motion, forward, backwards, or just up and down. In 2D, though, there are a lot more examples that are applicable to the real world. And in fact, much of the motion that we encounter in a day-to-day life in the real world is in fact 2D motion. So the examples here, driving a car. Now, when I drive a car, I don't typically just drive up and down the street forward and backwards. I might go north-south and then east-west, all on the same route as I go to work on a day-to-day basis. I might drive in circles if I feel like it. And then in the throwing the ball example, you know, usually when we throw balls, we don't just throw them up and down. Usually, if we throw a ball, it goes some distance and some altitude. So like throwing a football or shooting a basketball. All right, these are classical examples of 2D motion, and you can sort of go on from there. The one that physicists like are when we talk about launching cannonballs. I can imagine being, you know, medieval times, the physicist in charge of determining the launch angle for the cannonball that I'm going to shoot through the enemy army. Those are the glory days of being a physicist, I guess. So those are all examples of 2D motion, and there are many, many more that you can list, and we'll deal with a lot of these. But the important thing to remember is that the rules that apply to 1D motion, the rules that we've learned about and studied so far, those same rules apply to 2D motion. And in fact, there's no difference between the rules as we apply them to 2D motion. So this is sort of the key. Yeah, we've studied the simple scenarios. Now we're going to make it a little bit more complex, but we can use the same things that we've learned about so far. Now, the one thing that we have to worry about is before we can apply those rules, we have to do a little bit more work on the front end and dealing with the quantities themselves, the vectors themselves, before we can move on. So before we get into applying the rules to 2D motion, we're going to talk a little bit more about vectors. So as we've said from day one, vectors are numbers that have both a magnitude and a direction. Now in 1D, we've been limited to two choices of motion. You can either move forward or backwards. There's no forward and left or backwards and right. But in 2D, we open up a whole bunch of new possibilities. For example, I could move forwards with my object. My object could also be moving right in the same as it travels from point A to point B. Or it could be moving on a diagonal, or if I get even crazier, it could move in an arc or a circle. So sort of a combination of all these directions. So in 2D, there are many, many more possibilities. And in the real world, many examples of motion typically occur in 2D, even if they seem like they might occur in 3D. So imagine that ball example. When a ball travels from point A to point B, that I throw a ball, that ball is traveling in a plane. It's traveling in 2 dimensions, up and down and forward and back. So the key thing that we need to realize now, and the key thing we need to know about and talk about before we can start getting into these problems is how do we treat the mathematics of vectors. And the key thing to remember is that we can't add vectors just like we do normal numbers. Right? Before we can add vectors together, we have to do something special. And the thing that we have to do is we have to break vectors up into something that we call components. Right? So you're going to hear me talk about this word components quite a bit. Right? And it's sort of an important word because throughout the entire semester you're going to be using vectors day after day, and you're going to be doing this day after day, breaking up vectors into their components. And once we've broken vectors up into their components, that's when we can start applying the rules of normal everyday scalar math. Right? So in 2D, in 2 dimensions, vectors vectors have 2 components. Okay, so you can imagine, you could imagine when you're having a scenario where you have two dimensions. You're working in two dimensions, and a vector is moving, a ball is moving up while it's moving forward. And the way that we write that, the notation that we use to write a vector in terms of its components is this, where I've written the letters a sub x and a sub y. And you'll hear me refer to the components of a vector in this way throughout the course. What I've done here is I've broken up the vector a into its components, ax and ay. Now in this case, ax, that refers to the x component of the vector a. And I'll write down a similar notation for vector b. What these stand for, each of these numbers, a sub x, b sub x, a sub y, b sub y, are the components of the vectors a and b that lie along the x and y axes. So in your coordinate system, the components that lie along the x and y axes. And we'll talk about this in a little bit more detail. So usually when we deal with the components of a vector, or a vector in general, that vector will either lie in a horizontal plane or a vertical plane. So here I've drawn the case where the vector lies in a horizontal plane, and we could define a coordinate axis in something like the north-south direction and the east-west direction. So you can imagine looking at a map, and our vector lies somewhere in that plane, and then our x component and y component, the axes, will lie in that plane. On the other hand, it could lie in the vertical plane. So this is the case of a ball flying through the air, where the ball travels both vertically and horizontally. But in the horizontal direction, it's either moving forwards or backwards or left and right, and not both. Right? It's not curving or anything like that. So we can draw an axis that is vertical and horizontal, and we refer to those directions maybe as up and down, and left or right, or something similar to that. In both of these cases, we've drawn our coordinate axes, and in general, we can refer to these axes, instead of using north, south, east, west, or anything like that, we just write down the x and y directions, just like you've been doing probably for years in other math classes and things like that. So we can generalize our coordinates to be, our coordinate system to be in the x direction and the y direction, and we get to choose is x left or is x up, is y north, where x is south or x is west, or something like that. That's our decision to make. But the key thing to keep in mind here, the most important thing that we're doing when we're setting these coordinate axes up, is we're making x and y to be perpendicular. Right? The axis of our coordinate system are perpendicular. Now you've always probably drawn your coordinate system this way, and you've done it this way for a very important reason, and it has a little bit to do with motion, in fact. One of the reasons that this is important is because when you have coordinates that are related in this manner, and that they're perpendicular to each other, the motion in each direction, so for example the motion in the x direction, is independent of the motion in the other direction, so the other direction being the y direction. So if I have some motion taking place in the x direction, that has no effect, no influence on the motion that is taking place in the y direction. And what that means is that I can create the two components of the motion completely separately. So I can handle the x component of the motion without even worrying about the y component of the motion. And that's really, really important. And the reason that we can do that is because our x and y axes are perpendicular. So 2D problems exploit this idea. 2D problems, in order to solve 2D problems, what we're going to do is we're going to make use of the fact that this is the case, that the two directions are independent of each other. So what we're really trying to do is, instead of solving a single 2D problem that is a vector problem, it's a vector two-dimensional problem, right? Instead of solving that in one fell swoop, now what we're going to do is we're going to break that one problem into two 1D problems. And not only are they 1D problems, but they're two 1D scalar problems. Okay? So you're taking a single vector 2D problem and you're breaking it up into two 1D scalar problems. And when we do that, we can use the math that we've come to know and love throughout our entire life to solve that one-dimensional scalar problem. Adding is adding, subtracting is subtracting. So we're taking a problem that is inherently complicated and we're breaking it up into two different parts, but in the process we're making it simpler to solve. So in order to illustrate this, we're going to continue on and take a look at how to do this via an example. So we'll do that next. Okay, so here's an example problem with dealing with vectors in 2D, and we're going to start off simple with a single vector. And the question is this: in order to get to Eastern from Pulowski's house, you have to drive a car at 140 kilometers per hour in a direction 10 degrees south of east. And the question is, how long does it take to go 17 kilometers east? So notice here, I'm driving my car at some angle to the horizontal direction being east. So I'm not driving straight east, but the question is asking, how far does it take to go a certain distance east? So I've got something a little bit different going on here, something different than what we've done before. So in order to do this problem, what I need to do, and this is how we're going to approach all of our problems from now on when we're dealing with vectors, with two-dimensional vectors, is I have to do something to my velocity vector. And you can see I've drawn my velocity vector here as this straight line that goes from the car to Eastern. Now, before I get into anything, the first thing I always have to do when we're doing problems is set up a coordinate axis. And so just by choice, I'm going to set the horizontal direction to be the x direction, the vertical to be the y. And once I do that, I can start to draw in what is going to be components of my vector. So the first thing I need to do is break up my vector into components. So what you can see here is when I do that, what I'm going to do is I want to project my vector down into the x and y directions. And so I've drawn in what I'm trying to do right here. And let me blow it up a little bit so that I'll blow up the triangle so that you can see this a little bit more clearly. So here's my vector v, and I need to project my vector v into first the horizontal direction, or the x direction, and then the vertical direction, or the y direction. And what these components are, vx and vy, are just that. They're the components of my vector v. And if you look at this shape, you can see that, hey, it's a right triangle. What we talked about a couple days ago, I told you you're going to have to be using right triangles and doing all sorts of trig things. So graphically, I've broken up my vector. Now I keep saying this word projection, and so what do I really mean by that? The best way to illustrate that is to draw this little flashlight here, and imagine this flashlight spitting out some light. And that light, if you shine it at this vector v, which imagine is a stick, it casts a shadow. And the shadow that it casts is this horizontal shadow. And that is the component. I'm projecting the vector onto the horizontal axis. That's what it looks like. If I did the same thing, if I put the flashlight from the left, I would get this vertical shadow. And that's my y component of the vector velocity. So with those two components of the vector, all I need additionally to that, in order to solve for the actual numerical value of those components, is an angle. I need an angle, just like we talked about before. And if I know one of the sides and I know one of the angles, then I can figure out the other two sides. And so that's what I have here. I know the vector v, and I know the angle. And then once I know those velocities, then I can go back and solve my problem using this distance that I have, 17 kilometers. Now in the problem, the 17 kilometers only applies to the x distance. And so all I really need to solve this problem is the velocity in the x direction. The velocity in the y direction has no bearing on that 17 kilometers. But we'll solve for both anyway. So let's do that. Here I've written vx and vy, and so what I'm really solving for are the components of my vector v. And in order to get these components, I just need to use my trig identities. So if you think back to your math review, your trig identities, you should remember. Remember how you find the sides of a triangle if you know the angle. And so the mnemonic that you should remember from elementary school is so katoa, where that tells you the relationship. So is the sine of the angle is equal to the opposite over the hypotenuse. The cosine of the angle is equal to the adjacent side over the hypotenuse, and the tangent is equal to the opposite over the adjacent. Right? So that's what that's what you need to remember, and that's the trig that you need to know. So let's start off by solving for the x component of the velocity. I know the angle is 10, and I'm trying to get vx, and I can relate that to the magnitude of v, which is the hypotenuse of my triangle. So the equation looks like this. If I'm solving for vx, the velocity isn't 17, sorry, let me erase that. If I'm solving for Vx, the x component of the velocity, that is 140 kilometers per hour. All right, so 140 kilometers per hour. And then in order to get the x component, I need to multiply that by the cosine of the angle 10. Okay, so that's the angle that I need to multiply. All right, and then if I solve that equation, I find that the x component of my velocity is 137 kilometers per hour. I can do a similar thing in the y direction. My y direction is the side that is opposite to my 10-degree angle. If it's the opposite angle, I'm going to use the opposite and the hypotenuse. Then I need to use the sine. So the equation is going to be 140 kilometers per hour times the sine of 10 degrees. And then if you do the math for that, you'll find that the answer is something like 24.3 kilometers per hour. Right? So what we've done here is we've taken a vector velocity that's 140 kilometers per hour, and we've broken that up into its x and y components. The components of the vector that lie along the x and y axes. All right? And we solve for the length of those components. That's all we've done. But once we've done that, now we can apply our normal math skills. And just to make sure that I'm clear here, I want to show you where this equation came from, because I kind of skipped over that really quick. So if we go back and we look at our trig identities, remember cosine of theta is equal to the adjacent side divided by the hypotenuse. So here in this case, the side adjacent to the angle is Vx, so the x component of the velocity. And the magnitude of V is the hypotenuse. Similarly, when I solved for the y component of the velocity, I used the sine of the angle. So the identity there is sine of the angle is equal to the opposite side, which was Vy, divided by the hypotenuse, in this case, the magnitude of the vector velocity V. All right, so that's just to make sure that we're all on the same page and following what I did to get the components of the velocity. Okay, so now that I have these velocity components, now I can, like I said, go back and actually use my normal scalar math to solve for the time it takes, the distance traveled in some amount of time. So I can use what we've already learned about 1D kinematics and solve for my time, or my distance. I'm sorry, my time. So I know the x component of the velocity, and I'm given some distance, and I can, using the equations that our basic definition of velocity, I can go back and solve for time. Now, of course, I gave you a displacement. I gave you a delta x, and so our delta x from above is actually 17 kilometers. So I know that the time is equal to 17 kilometers divided by the velocity that we just solved for, or 137 kilometers per hour. Okay, and so if you have those two numbers and you do the math, or actually first we should check our units, which I'm doing as we go along here, so I can see that a kilometer divided by kilometer goes away, and I'm left with hours on the numerator, so I'm good with my units. And if I do the math, I get 0.124 hours. And then if I convert that into a more reasonable unit, maybe minutes in this case, I get 7.45 minutes. And so the last step of solving all physics problems is to check that makes sense. And so if I'm on a 7 minute, seems to make sense if I'm driving very fast and I'm not getting stopped by stoplights and people aren't driving in the left-hand lane, etc. So that seems like a reasonable answer. All right, so the next thing to take a really quick look at then is to ask yourself about, okay, well, how does that relate to the original vector velocity? Do I get that velocity back somehow? And the answer is, well, I can get the magnitude of the velocity back by using Pythagorean's theorem. We have a right triangle here, and the right triangle has sides that are length Vx and Vy. So if I square those things and take the square root of the result, I get the magnitude of my original vector V. All right, just like we talked about in math review. And then, if I know the magnitude of the vector V and I know the sides, well then I know everything I know about the triangle. And so now I can use my inverse trig identities, if I want to come up with the angle theta. So the angle theta, which I know is 10 degrees already, but let's call it theta, and just pick one of our favorite identities. So I'll pick sine. If I take the inverse sine of the opposite, which is Vy divided by the hypotenuse, which is the magnitude of V, then I could get my angle theta. So I'm not going to solve those because we already know that information from the problem statement. But that's how it's all related. And you'll find that during the course of the semester, throughout the semester, you're going to be doing this sort of thing time and time again, where you'll start off with a problem that has several vectors, and you'll need to break those vectors up into their vector components, x and y components, solve for a bunch of math stuff, and then take the result, the final vector, the resulting vector, and put that back into, use Pythagorean theorem to get a magnitude and a direction at the end. Okay, so let's go the next logical step then and talk about how we do mathematics with a vector. So how do we go about adding and subtracting vectors? Right. So now remember that I said from day one that when you're dealing with vectors, you can't just use normal math. Normal math doesn't work. You have to use vector math. So let's take a look at this illustration and try to see what I mean. All right. So here are two vectors. Vector A is pointing up. Vector B is pointing to the right. Remember, they have magnitudes and directions. So I'm going to give you the magnitudes of these vectors. We'll call them 3, and we'll just say 3 units. And so I'm giving you magnitudes. And then the magnitude of vector B is something like 2 units. Okay, we'll just kind of ignore units right now. So the question is, if I'm going to add those two vectors together, what is the result? So I want to add vector A plus vector B. So the question is, well, I mean, if we're using math, we'd say, normal math, we'd say the answer is 5. But, you know, from what I've been telling you, we know that the answer can't be 5, at least not in this example. And the reason that that answer isn't 5 in this case, because, well, direction is important. If direction weren't important, then I wouldn't be telling you anything about this. All right, so direction matters. All right, and so let's take a look at a couple other simple illustrations just to highlight this point a little bit further. All right, so I'm going to draw the vectors A and B once again. Vector A and vector B. In this case, I'm going to line them up to be pointed in the same direction. And so what I want to do with these two vectors, and I'm going to draw a couple different cases, I want to add them together and see what the result is. All right, but before we do that numerically, let's see how you do it graphically. So whenever I'm adding two vectors together graphically, the rule is to take the first vector and place it where it is, and then you move the second vector to the end of the first vector. So I attach the tail of the second vector to the head of the first vector. And that is graphically how we add vectors together. And you can see what I've drawn here is a third vector C, which is the result of A plus B. And C starts at the beginning of the first vector, and it ends at the end of the second vector. So I've added those two vectors together, and I'm going to call that vector C. And then over here in the third column, what I'm going to do is I'm going to write down the magnitude of my vector C. All right, so I'm going to add the two vectors together graphically, and then I'm going to write down the magnitude based on the orientation of the vectors. So in this first case, since they're both pointing in the same way, then the magnitude of the vector C is just 5, because I add them together. The vector components are equivalent to the magnitude of the individual vectors, so the total length of the vector is 5. But if I do something a little bit differently, so this is kind of like the initial example there. If I draw vector A to be horizontal, and then I draw vector B to be vertical, I'll just draw it down to be different. Now I get a slightly different answer. So now, again, I'm going to add them graphically. So I draw down the first, and then I put the second vector, I stick the tail of the second vector to the head of the first vector. And then my resultant vector, which again I'll call C, I start that at the tail of the first vector, and then it ends at the head of the second vector. Right? So that's vector C. In this example, because you know enough about triangles and straight lines and things, you can see that the length of vector c is not going to be 5. And in fact, in this case, if you use Pythagorean Theorem to find the length of vector c, you would find that it's 3.6 units. Right? So in this case, it's certainly not 5. It's a bit shorter than 5. So we'll take this one more step. We'll go to sort of the next extreme, which is, okay, I'll draw vector A again, and this time I'm going to draw vector B. But vector B is going to be anti-parallel to A. Right, so now it's pointing backwards. Now if I add these two vectors together graphically, once again I draw A going from there to there, and then I stick B on the end of A, so the tail of B touches the head of A. Vector C now is, once again, it's going to start at the tail of A and go to the head of the second vector. So this is vector C. Right? And so vector C is much shorter than either of the other two vectors. And then if you do the math, because these two sort of lie in the same line, what I'm doing here is basically subtracting the magnitude of vector B from A. What I get is 1. Right? So I get a length of 1. Is it 1? Yeah, 3 minus 2, yes, 1. I forgot the length of my vectors there. So 1. We get a length, C magnitude of C is 1. Right? So what you can see here is, depending on the direction of the two vectors relative to one another, the magnitude, the answer, is different. And so that's why you just can't use normal math to add the two vectors together. Right? In each of these three cases, I had to do something different. In the first and third case, or in each of these cases, what I essentially did behind the scenes is break these vectors up into their vector components. But because these vectors in each three cases are either parallel or perpendicular, the vector components are the same as the actual magnitudes of the vectors themselves. They just might be in different directions. Okay, but let's take a look of what really was going behind the scenes by focusing in on this perpendicular example. I'm going to do this really explicitly so we can start to see what's really happening here. So here's the picture where I've drawn A and B and then the resultant vector C. And what I'm going to draw then is two columns where I'm going to list the vector components in the x direction and the y direction separately. So I'm defining my x and y axis like so. And I'm just going to write down exactly what my vector components are. So for vector A only lies in the x direction, so the x component of the vector A is 3, the y component of the vector A is 0. For vector B, it only lies in the y direction, so the x component is 0 and the y component is 2. And so now I can add these together, because once again, I've broken them up into their components, and now I can add them together. So C then has a magnitude in the x direction of 3 and a magnitude in the y direction of 2. So I get this vector C that has a component in both the x and y direction. So if I'm using my vector notation, I can write that down like this. Vector C is 3, 2. 3 units in the x direction and 2 units in the y direction. So this is an okay vector notation to use. This actually is a vector. It both has a magnitude and a direction. Right? Magnitude and direction. Now, in physics, typically though, we write this a little bit differently. What I could do is, instead of writing it in this notation where there's two magnitudes and I don't really know what the direction is, I can actually write down the magnitude of the vector and the direction separately. So in order to find the magnitude, I use Pythagorean Theorem. So a length of one side is 3, length of the other side is 2, and I already know that the magnitude is 3.6 from my table above. And then I can find the direction, or theta. We'll pick theta to be this angle, and that's going to be equal to, let's use the, what are we going to use? We could use the sine, tangent, or cosine. Take your pick, because we know all three sides. I'll pick the sine, so the inverse sine of the y component of the vector, which is just 2, divided by the hypotenuse, which is 3.6, will give me the angle. And the angle is, if I take a look at my notes, 33.8 degrees south of east. Right? So I've gotten everything that I need to correctly write down my vector. So in physics world, the way that we typically write down the solution is the vector C is 3.6 meters, we'll call it meters, at an angle of 33.8 degrees south of east. So that's typically how you'll see the solution written down.